Hi, my name is Michael Ostroff and I am a PhD student here at FAU. Today, I would like to talk to you about what is known as complex Riemannian manifolds. These are actually distinct from what are conventionally known as complex manifolds in several different ways. In fact, they are a lot more similar to normal real manifolds you would find in general relativity than complex manifolds. Before I get to them, I need to start with an analogy. You're all familiar with the wave equation, I would assume. Like, imagine you take a rock and you throw it into a pond, and you can see how the waves ripple outwards from that. Like, that's essentially how the wave equation works, where the system evolves over time. And so when we normally think about it, we think of it as like having a real value defined everywhere for real coordinates. And this like acts exactly as how we expect it would. And you could take some like real function, which like, actually you could take a meromorphic function, I should say, and that like you can plug in like CT and X as like two coordinates, and you could make it such that like for real values, it like gives a real result, and it abides by the wave equation essentially. But you could then take that meromorphic function and start plugging in complex values. And when you do this, like it's still like a perfectly well-defined system, but now instead of getting like real values out, you're getting like complex values out. And you've essentially like generalized like the wave equation, like the 2D wave equation, into like the complex coordinate system. But as we know, it still behaves exactly the same way for those real coordinates. So this is still like a 2D system at heart, and it like works the way you would expect it to work essentially. It's just that now it works for like complex values as well as like real ones. So this, you can actually do this with not just like the wave equation. You can do this with any analytic PDE or like yeah, in general. So you could take something like the two-sphere, which there's a nice simple equation for it, which only depends on like theta usually, like that's and you could, instead of plugging in like real values of theta and phi, which doesn't affect the metric, you could plug in complex values, and you would have essentially what is a complex Riemannian manifold. Like the normal real manifolds in general relativity, these complex Riemannian manifolds, they're still symmetric. Like they don't become like Hermitian or anything, just like symmetric in both like the real and complex components. And as a result of this, you can actually like still use the Levi-Civita like connections equation in order to get the Levi-Civita connection from the metric tensor field, even though it's complex. It does not cause any issues whatsoever. And since you now have the Levi-Civita connection and it's analytic, and derivatives are still like very well defined because it's, well, analytic, then you can then go and find what the Ricci curvature is, and you could find like vacuum solutions and all sorts of stuff, or maybe match, and like in the case of that complex two-sphere, it would essentially like have like positive curvature like you would expect. Like let's say it's like the curvature is 1 everywhere, like regardless of the coordinates. Like even though they're like complex, it doesn't cause any issues whatsoever in this scenario. There's a really simple, like basic and trivial example of a complex Riemannian manifold, and that is essentially what I call a complex one-sphere. It essentially has the metric 1 divided by z squared, or no, it has the metric negative 1 divided by z squared. And if you were to plot it on the complex plane, you would find that it has a singularity at z equals 0. An interesting, like this manifold has a lot of interesting properties. So geodesics, like if you were to like go like on a geodesic around the center, let's say this is 0, z equals 0, then the geodesics would be like essentially closed circles. But you could also like go off on an angle and let's say like spiral inwards instead. And if you were to like use the symmetric tensor and you were trying to like find the distance, that reminds me, I forgot to talk about distances on complex Riemannian manifolds. Okay, so for complex manifolds, the distance is always like real, essentially. But for complex Riemannian manifolds, you calculate the distance essentially like you would in like general relativity. But because there are like complex numbers, it can get a bit confusing, but it doesn't really matter. Essentially, when you like are trying to find the lengths of a vector in general relativity, you take it, you multiply it by the metric tensor in order to make it like a covariant, and then you take the dot product of it, and it's a covariant and contravariant like selves together to get essentially the absolute value of that vector. And then if you want to find the lengths of that, you basically just take the square root. So everything before the like square root part is like still like perfectly well defined on like complex Riemannian manifolds. The square root part leaves an ambiguity of a plus or minus 1 in the result, but that doesn't really matter too much for what we're doing. So going back to the like complex 1 sphere, if you wanted to find what the distance between like some part over here and like z equals 0, then because of that singularity at like z equals 0, as you like go in, oh, I should mention, the singularity at z equals 0, that's not like a problematic black hole like singularity, it's a coordinate singularity. But despite being a coordinate singularity, it's actually impossible to remove it. More on that. Okay, so if you were to take the length element and integrate it from like the singularity to any other point, essentially you would find that it would come out to like a distance of like complex infinity, which means that this coordinate singularity at z equals 0 is actually infinitely far away from every other point, essentially. And as you approach the singularity, for this manifold that I gave an example of, if you were to try to find the circumference around like the center of it by like going and chart like around the center like this and coming back to your starting point, and you were to measure how long that would be, you would always get the lengths 2 pi. You can like scale the metric up and down to get like different values, but for the one that I gave, it'll give you 2 pi essentially. And this is regardless of what your coordinate distance is from the coordinate singularity at the center. So if you were like astronomically close to it, like 10 to the power of like negative 99999, and you went around the center, you would still get the result 2 pi. And if you were like at coordinate 10 to the power of 99999, like all like very far away coordinate wise, and you went around it, then you would still get the same answer of like 2 pi as the circumference. Anyways, so as you like approach singularity, like that property of the like complex 1 sphere, it does not change whatsoever, and nothing really breaks down as you approach the center. And because of all this, it being like infinitely far away, it being like a coordinate singularity, I think that it counts as a conformal boundary. So this, like when you normally think of like a boundary of like a manifold, you might think of it being on the exterior and surrounding like the interior components. But for the complex 1 sphere, it has the boundary at its very center, which is very peculiar. I should also mention that this complex 1 sphere, it allows you to embed a one-dimensional manifold in a 1D space-time, essentially. Because like the complex, oftentimes when we think of like complex spaces, like we think of it as like, oh, it's a complex plane, and that sort of terminology makes it sound like it's like the complex plane is like 2D, but actually it's still only one-dimensional. Like complex numbers can be a bit confusing and tricky, but this has I think this might have a connection with what's known as Whitney's embedding theorem. Essentially, it states that if you have an n manifold, you can always embed it in at least 2 n real dimensions. And this means you can like let's say you have like a circle, and it's like a one-dimensional manifold, and let's say you were confined to like real dimensions. If you wanted to embed it, you'd have to embed it on a plane. And if you had like a sphere, like a 2-sphere, then you'd have to embed it into 3D spacetime as like the surface of like a 3-ball essentially. So Whitney's embedding theorem says that if you have an n manifold, you can embed it in like 2n real dimensions where it's not going to intersect with itself. And because we like to think of complex spaces as being twice the dimensionality of real ones, it occurs to me that it might be the case that you might be able to generally embed n manifolds in like ND complex space. I have not proved this. I'm not a mathematician, I'm a physicist, so I really haven't like thoroughly like tested it, and I don't really think I'm capable of thoroughly testing it, but it's probably like mathematicians should probably look into like complex Riemannian manifolds and see if they're useful for stuff like this. Anyways, there's this thing called Kaluza-Klein theory, and basically it states that if you have general relativity with like extended dimensions and you add like dimensions which are like compactified, basically like products manifolds, basically have your like normal extended manifold, and then you have like closed manifolds or compact spaces actually, and you product them together essentially with like the other manifolds, then it creates essentially these like gauge fields. If you do this with the one sphere, then you get electromagnetism, and that's like normally like known as like the 5D Kaluza-Klein theory. So this complex one sphere, that allows you to essentially, if you were to product it with like Minkowski spacetime, that would give you like that 5D Kaluza-Klein theory, but now you have global coordinates. So you can plug in whatever like coordinates you want, and it should be like well defined. It's not like periodic coordinates where like you go a certain distance and then it like loops back and you can't like plug in any values other than those. Basically, these complex Riemannian manifolds, they allow you to get Kaluza-Klein theory with like these what I feel are like more mathematically well behaved global coordinates. I would like to talk about the ADS-CFT correspondence. So I'm a classical GR physicist kind of person. I don't really do like quantum stuff, so I don't have the best understanding of this, but I know that the reason that the ADS-CFT like correspondence, like one of the reasons it works is because there's a conformal boundary for like the ADS space-time stuff. Like if you were to take this Minkowski space-time and product it with the complex one sphere, because that actually has a conformal boundary at the center at z equals 0, I think that could be a conformal boundary you could use to sort of generalize the ADS-CFT correspondence to Minkowski space-time. So for the ADS-CFT correspondence, if my understanding is correct, quantum mechanics and all that sort of stuff, that happens at the boundary, essentially, the conformal boundary. And for this case, I think that, or for the case of the complex one sphere, I think that if you were to just take our universe and all like the fields and stuff, and you were to then just zoom in on that singularity more and more and more, you would essentially all of our universe, essentially everything which goes on inside of it, like the quantum mechanics and other stuff, that would essentially be lying basically on the singularity itself, as you zoom in infinitely in this complex plane. So, that's where our universe essentially exists and takes place. And because I'm not a quantum physics person who's familiar with the ADS-CFT correspondence, I myself don't know how it can be generalized to work using the complex one sphere. But I think if you're watching and you're familiar with it, you should try. I made a blog post on my blog which is titled Unconventional Complex Manifolds, which is what I was calling these complex Riemannian manifolds before I realized that they were discovered prior to me. So you can like look at it there and like learn more about it. Also read the correction note that I added, stating that these have been known since like the 1980s. Like Claude Lebrun, a student of Penrose, I believe, actually published their dissertation on these complex Riemannian manifolds, and I think 3 years later they published like another revised paper on them as well. So I linked to those, and like you should like look at them, and like these aren't like these complex Riemannian manifolds, they are still being researched to some extent. So these complex Riemannian manifolds, they are still being researched, like not that much, like very infrequently, because like they're extremely poorly known compared to their siblings complex manifolds. But Soren Dumitrescu has actually published some papers about it, like them this millennia. I don't know if they've really published anything like particularly recent. I'd have to like read through like all their work to like figure out if like any given publication is like regarding them. But there were some in like the like 2000s that were published, like at least 2. So I linked to some of those in the blog post as well, in case you're curious. So should these, like the takeaway from this is that like these complex Riemannian manifolds, they have interesting properties and should actually be researched for once. And one of the interesting things that you can do with them involves wormholes. So if you have a like imagine a donut, like the surface of a donut, like that is a 2 torus. Okay, if you have a 2 torus, imagine you want to like flatten it onto like a plane or whatnot, so you like can embed it in like 2 dimensions instead of like 3 dimensions. That is not really possible to do in real dimensions, but if you move into complex coordinates, then you can easily do this by producting 2 complex 1-spheres together. And you could imagine that this complex 2 torus is actually the cross-sectional topology of a 2 torus wormhole. If you were to have this, then it would essentially be a Ricci-flat manifold, which means it does not require any like exotic energy or whatnot to stabilize it. So you could have, let's say, a like 2-sphere wormhole mouse over here and a 2-sphere wormhole mouse over here, and connecting these, like going through like complex coordinates, is this like complex 2 torus wormhole. And it could be like embedded like what was in like the coordinate system, such that you could go from here and go through like these complex coordinates and come back out at another like point in space. And from your perspective, you didn't go like that like far, but from like the perspective of someone who's unaware of the wormhole, you could move like a vast amount of distance. And so these like distant regions of space-time, they're like even though they're like distant, they are like essentially like connected essentially locally in a way, because like let's say like the wormhole's throat is actually like very short, like then the Bose mouse could be like considered like local with respect to each other. From the coordinate system, like even though it from the coordinate system's perspective, this is technically a local connection, but from space-time's perspective, it looks like a non-local connection. It's this like weird combination, like I call this like property like this oxymoronic property, like local, non-local, and this actually kind of ties in with like quantum mechanics, because in quantum mechanics, there's this thing called Bell's inequality, which quantum mechanics violates, and essentially like this means, like if you were, like this isn't a video about like Bell's inequality per se. There's a lot of good ones on YouTube, but essentially the general takeaway is like quantum mechanics either has to be non-local, or non-local real, local non-real, or there has to be like statistical dependence between like various different events. So basically, local means like like you can evolve the system with like local knowledge essentially, but real means it's like deterministic here. Like I guess in this case it's like, in the case of what I'm doing, it's technically like complex, but whatever. Because like we have this like wormhole, like hypothetically, this like complex two torus wormhole, we could connect two distant regions of space-time in a way where space-time thinks it's non-local, but the coordinate system thinks it's local. So that would essentially allow, and because it's like still like deterministic, this would essentially be this local non-local connection, which would violate Bell's inequality whilst preserving realism and locality. Technically, it's kind of confusing. So I'm kind of rambling, so I didn't explain it particularly good. I'm going to make a blog post on this, like hopefully soonish, and hopefully that explains like the idea better. But essentially, like complex coordinates allow you to essentially, or could essentially allow like classical GR to violate Bell's inequality, and therefore there's like not really much standing in the way of potentially creating a theory of everything where quantum mechanics and general relativity sort of like get along, and potentially quantum mechanics is derived from general relativity. I suspect that's something you can do. I have not managed to do that yet though, but that's something I'm working towards, I suppose. Essentially, complex Riemannian manifolds allow you to violate Bell's inequality in classical GR, like via this like weird like local locality thing. Oh, I probably should have mentioned this earlier, but all meromorphic real manifolds are also like complex Riemannian manifolds. Let's say you're an ant on a two-sphere, and let's say there's also another time dimension which I can't really like visualize, so it's technically like 3D, but it's 2D, and you're an ant on like this two-sphere essentially. This ant is an observer, and they observe this like 2D environment around them which like evolves over time, and like so everything looks two-dimensional. They like observe like some waves, like, and they act in like the expected like 2 + 1D like manner essentially. Everything's all normal and good. That is for the real coordinates for both like phi, theta, and like CT. But you could plug in complex coordinates and you'd be able to get like results out as well. So if you wanted to find out what the value of the metric tensor was for some complex coordinates, you could just like plug it into this like meromorphic metric tensor, and you would get the like resulting metric tensor at that location, and it would have complex values in it. And so despite the fact that they're like, we might think of like this like 3 complex dimension space as like 6 real dimensions, it's not. It actually behaves 3D essentially. It like adding complex numbers into the mix doesn't like double the dimensionality like automatically. That's not how it works. Complex structure actually like imposes so much structure on the like fields that it still looks the same dimensionality. It's weird, but that's kind of how the mathematics ends up working. You can like show that this is correct by trying to like create a counterexample. because like people, so you know how you can create like a 1 + 1D like wave equation in 2D. Well, someone might look at this like complex plane, say, oh, that's actually 2D, and if they try to go and recreate that wave equation on that what's technically a one-dimensional like complex plane, they won't really be able to do it with out like the complex structure like getting in the way. What I'm trying to say is like complex dimensions aren't actually double like the dimensionality of real ones, but basically because you do kind of in a way have more space, it allows like more ways to like structure things around. It's like a weird middle ground essentially. I've came up with this concept in relation to these complex Riemannian manifolds of what I'm calling submanifolds and like submanifold transport. If you go back to that complex one sphere, like it's clear that if you like move tangent to this like circle, like if you're on like this point and you like go on a geodesic forward, you're just going to stay along this circle. And I consider that like a submanifold, like the actual like one sphere like submanifold. However, you could just as easily go perpendicular to it. It's not actually perpendicular, and just like go inwards towards the center or like outwards towards infinity. But so like I've came up with this like because it's like you can, if you like do like if you're like moving in this direction and you have no component like in the coordinate space towards the singularity, you're always going to stay on that circle. And that caused me to come up with this idea, which I refer to as submanifold transport, where you have a point in this like complex coordinate system or complex Riemannian manifold, and you have a set of vectors, and if you were to parallel transport along a real linear combination of these vectors, you would stay along like the submanifold essentially. And this submanifold would correspond to some kind of compact space or something like that. Or not, no, it doesn't necessarily have to be a compact space. You could do that with like Minkowski space-time and like subparallel transport along like a manifold in there. Or submanifold, yeah. Yeah, I think if you were like thinking about how do I embed any given like n-manifold in like complex space-time, you probably want to look at it from like the perspective of like submanifold transport, which is like parallel, it's like parallel transport, but on these like which like stays on these like submanifolds and doesn't like leap off of them. So it stays like kind of constrained, I suppose. So to recap everything we've gone over, I introduced you to complex Riemannian manifolds, talked about how they're different from like the normal conventional complex manifolds, which are very popular. And honestly, between you and me, I think it should be complex Riemannian manifolds, which are known as complex manifolds. I don't think that, like, I think that the complex manifolds are just like real manifolds pretending to be complex manifolds. I don't like them, not at all, not one bit. Anyways, introduced you to the idea of extending like analytic PDEs like into complex coordinates just by, well, inputting complex coordinates into them, and I talked about how like complex Riemannian manifolds relate to the like Whitney's embedding theorem, and the possibility you might be able to like take Whitney's embedding theorem a step further and embed like n manifolds in n dimensions, which would be like really, really cool in my opinion. Like, I'm not sure if that's like universally possible. Mathematicians, please look into it. I talked about how complex Riemannian manifolds allow you to embed wormholes into the complex coordinate system. So it's like you can have two different points connected, and it's like there are no like cuts or like there's no periodicity like required in the coordinate system. Everything stays nice and like smooth, meromorphic to be more exact. Like, I like it. It's very mathematically elegant in my opinion. Mentioned how like that allows like general relativity, classical general relativity, to violate Bell's inequality. I talked about submanifold transport, or submanifold parallel transport. In the next video, we're going to be talking about some of my other research, more of like a hobby of mine, to be exact. It's something which is known as fractal flow. It's something I actually discovered a few years ago. Yeah, it's essentially how fractals sort of like shift around as like their parameters change. Think of how like the Julia set shifts as like the value of C or like plugging into it changes. That will be the subject of the next video with me. Thank you and goodbye.